For Chapter 4, we're going to be talking a little bit more about molecules. Those are the things that we get when we put atoms of different elements together, and each different kind of molecule has its own chemical properties. We refer to those molecules in the larger scale as compounds, and we look at the chemical reactions that occur, which are the changes of one substance to another substance through the rearrangement of the attachments of the atoms and the molecules that are present. And so molecules are what's responsible for all of the behavior that we see for matter. Molecules make up the objects around us, the air, the countertops, our bodies, everything. And change from one type of molecule to another is what represents all of the change, for the most part, that we see around us. So now, this is pretty much the case. It's pretty much cut and dry. Why did it do that to me? There. And there hasn't been any real exceptions to this rule found in science. Now, we're going to look at chemical compounds. Let's make sure we're all on the same page with what a chemical formula is. Chemical formula. And a chemical formula is just the element symbols combined with subscripts representing how many of that particular element are present, and that shows the ratio of individual element atoms in a molecule. So, for instance, H2O, the familiar chemical formula of water, means 2 hydrogens. And the subscripts refer back to whatever element immediately preceded that subscript number. And an oxygen, if there's no number written next to it, we assume there's at least one, or else we wouldn't have bothered to write the element symbol. And that's it. They have 2 hydrogens to every 1 oxygen, and that's the ratio that makes up water. Now, we change the subscripts in a chemical formula. What we have is a different compound. And we can even have some really more complicated examples where the arrangement of the atoms is important, and we can have the same chemical formula, but slightly different compounds because they're connected differently. But what we're going to look at first is just some more straightforward compounds that we're not going to have to worry about the connection because they're going to be small, or they're going to be relatively simple in terms of what kind of molecules we'll look at later. We already said that H2O is water. We know what water is like. It acts like water. We drink it. We need it to survive. It's a main component as a part of our bodies. If we have a slightly different ratio of atoms, though, 2 hydrogens to every 2 oxygens, as we have in hydrogen peroxide, what we actually have is a very toxic substance that we can't drink without being injured. It oxidizes things, burns on cuts where water does not, has very, very different properties. And the only thing that's changed is instead of water being 2 hydrogens and 1 oxygen, hydrogen peroxide just has 1 more attached oxygen to it. So the formula makes up the molecule, and the formula helps us to understand the chemical properties. It defines what type of molecule, what type of substance, and what type of substance defines what properties that chemical will have. And so let's make sure we're on the same page again. If we have the formula for glucose, C6H12O6, how many of each type of atom do we have? Well, 6 is right next to the carbon, so 6 carbons. 12 is right next to the hydrogen, so 12 hydrogens. 6 next to the oxygen, so 6 oxygens. That's it. That's as hard as that is. So we have 2 basic kinds of compounds that we're going to talk about in this class. There are ionic compounds and molecular compounds. So elements have unstable electron configurations unless they're noble gases. The noble gases already have that full octet, that 8 electrons in the outermost shell, the valence orbital, so they're already stable. Everything else, they're going to have to do something to try to gain stability, either by sharing, transferring electrons, giving up and taking in those electrons. That's what an ionic compound is, one that has given up electrons from one atom and taken them in from another. Or we can have sharing of electrons, which is referred to as molecular compounds. And in the sharing of electrons, electrons stay on the same original atom. They're not given up or taken in by another one, but the electrons are actually shared between elements, and that gives us a point of mutual attraction for the nuclei, and resulting in a bond that holds the molecules together. So let's look at two quick examples of this to understand what's holding these molecules together. So in an ionic compound, we have sodium, and its valence orbital, if we work that out from the periodic table like we saw before, has 1 electron in it. Okay? So that 1 electron in that valence orbital, from looking at the periodic table and counting across and divvying up the electrons, 2 in the first shell, 8 in the next, 1 more in the third, etc. We can compare that with a chlorine atom, which has 7 electrons. We can represent those electrons by little dots, even though we know that they're both a particle and a wave from that previous other chapter. Okay, so neither of these two elements, or neither of the atoms of these two elements, have a completely full, stable electron configuration. So they want to do something to end up with a stable electron configuration. Well, inside the sodium, we actually have the n equals 2 orbit, right? And in the n equals 2 orbit, we have 8 electrons. So this n equals 3, 1 electron that's sitting here in the valence orbital, if that went away, we'd be left with these 8 electrons in the valence orbital, and we'd have a full valence shell, and we're good. That would be stable. So this wants to give up an electron. Goodbye. Okay. So when it does that, it's going to have 1 fewer electrons than it did. So that's going to create a mismatch between the protons and the electrons. And if it has 1 fewer negative object, that means that this particular sodium will now be an ion with a +1 charge. Alright, what about the chlorine atom? It has 7 electrons. It wants 8. So if it can grab an electron from somewhere, what we're going to end up with is a chlorine atom that has 8 electrons around it. Nope, that should be a dot. Now, so these 8 electrons give us a stable configuration again. But now if we've added an electron with the same number of protons present, that's 1 extra negative object, that's now -1 charged for that chlorine, and it's an ion, an anion, a negative version of ions. Well, if this is positive and the chlorine is negative, they're going to be attracted to each other just by electrostatic attraction. Positive things attract negative things. And that's going to form this attraction. The attraction is referred to as an ionic bond. And the molecule that they form, this ratio of sodiums and chlorides, is considered an ionic compound. Okay, so molecular compounds, where they share, instead now of having, let's see, what can I say? Instead of having electrons given up and taken in by something else, they're actually going to share the electrons between them. So let's look at a chlorine. I already said it has 7 valence electrons. And another chlorine. And they each have 7. But if they could somehow share these electrons between the two, then we could say that they each have 8 electrons. They're sharing one of the other atom's electrons, but if overall they would have 8 and they would be stable. So when that happens, those 2 electrons, one being shared from each of the chlorines, are located between the nuclei, that positive set of protons in the center, right? So the positive set of protons is attracted to the electrons, and the electrons are attracted to the positive protons on both sides. So that mutual attraction to these electrons, the protons attracting those electrons, pulls these atoms in together and keeps them bonded together, keeps them attached. So this is referred to as a covalent bond. Why? Because it has valence orbitals, and those valence orbitals are shared cooperatively, so it's a covalent bond. And we'll get into much more detailed explanations of how these bonds look and form a little bit later. But for now, I want you to know these 2 definitions: shared, covalent, molecular compounds. Given up and taken in, lost and gained electrons, ionic. Ionic bonds, ionic compounds. Ionic compounds, if we look at the periodic table, is going to contain a metal and a non-metal. And the reason for this is metals tend to lose electrons. Right? They're on the left side of the periodic table. They only have a couple of valence electrons. And if they lose those, what we're going to end up with is the last orbital shell before the one that they used to have electrons in, that 1 or 2 electrons that the metal had, and that previous shell will already be full from all the other electrons. So metals lose electrons, meaning that they tend to form positive ions. Nonmetals are on the other side of the periodic table. If they gain an electron or 2, then they're going to be like a noble gas and have a full outermost valence shell. And if they're gaining electrons, they're going to end up more negative than they started, so they tend to be negative ions. Positive and negatives, ionic bond. Okay? The subscripts in the compound, again, just represent the ratio of these elements in a crystal lattice. For ionic substances, we don't actually have a discrete, say, sodium chloride bonded together, and then somewhere else another sodium and a chloride bonded together. In reality, what we have is the sodium attached to a chlorine, attached to a sodium, attached to a chlorine. This is a 3-dimensional shape. So this whole 3-dimensional cube array, like we see here, is actually what we end up with ionic compounds. And different ratios and different arrangements of these lead to different crystals. Right? Ionic compounds are the ones that you typically see as crystalline, like sodium chloride, and calcium, and all sorts of other types of metals and non-metal combinations. They make salt-like substances. Another name for ionic compounds is salts. Sodium chloride being table salt is a really commonly known example of that. Some of these are what's referred to as soluble. Soluble ones break back apart again in water. And the reason they do that is these little water molecules have a slight charge to them also, not because they've gained or lost electrons, but just because of how the electrons are shared inside of a water molecule. Water molecules are kind of more covalent, although they have a little bit of an ionic character to them as well. But in any case, those water molecules will surround the ions, and the slightly negative and slightly positive parts of those water molecules will help allow the sodium and the chloride ions, or the positive and the negative ions, drift apart from each other and still be stable. And so when you have ions like this dissolved and dissociated inside water, broken back apart again, We refer to these as electrolyte solutions, and the reason we refer to those that way is because they conduct electricity. Now, molecular compounds, these are going to contain only nonmetals. Okay, so only things from the right side of the periodic table. While before with ionics we had a left side and a right side element, here we have one or more right side elements only. And like I said before, they're shared, not always equally. The resulting bond we said is called a covalent bond. The subscripts actually represent the real, true, actual number of each kind of atom in a molecule. And now molecules are discrete. If we have water, for instance, H2O, that means we have a hydrogen connected to an oxygen, connected to another hydrogen. And this molecule floats around, and some other discrete, completely separate, not attached additional two hydrogens and an oxygen attached together through a bond is floating around with it. So instead of having this crystal lattice of repeating three-dimensional alternating bonds like ionic compounds do, molecules are discrete. They're their own unit, basically. That doesn't mean they can't be enormously large and complex. This is a hemoglobin molecule. This whole thing is just one set long series of connections all attached to each other, and this is the protein that's responsible for transferring oxygen around inside of your body. So we have very simple molecules with just a couple of atoms like water. We have extremely complicated molecules with thousands of atoms like hemoglobin. And so all of these properties, the properties of the elements that you see, are caused by the composition, caused by what's in the molecules. So specifically, it's made up of what atoms are present, how those atoms are arranged in terms of their shape and structure of their bonds, and what kind of bonds they have in the first place. Little changes can make a pretty big difference. I mean, we can look at the difference between propane, made up of carbon and hydrogen in a 3:8 ratio. So there's actually 3 carbons and 8 hydrogens. Now if we look at the connections, we have a bunch of carbons connected in the middle of a molecule, bonded to a bunch of hydrogens that kind of cap off the outside of the molecule. And this is propane. Propane, for the most part, we use as a gas, or as a very volatile liquid that turns into a gas very quickly. Now octane is a major component of gasoline. Those molecules are actually 8 carbons with hydrogens. I'm not going to draw them in, but I'll draw the lines to them all around the outside. So that gives us a C8H18 molecule, and that's a liquid at room temperature, even though propane is a gas at room temperature. So even though they're both only carbon and hydrogen, one of them being a little bit bigger means that it's going to have different types of properties. Okay, so let's look at each of these and decide whether this is ionic or covalent. And to do that, pull out your periodic table. Are we looking at something that's left side, right side? If so, it's ionic. Are we looking at two things from the right side? If so, it's covalent. That's as difficult as it is. The reason we want to be able to identify this is not only because ionic and covalent compounds have different properties, but when we name the compounds, we're going to have to learn how to name them based on rules that first have to differentiate between whether or not an ionic compound is what we're describing or whether it's a covalent compound we're describing. So let's look at our first example, sodium bromide. What is it? Well, sodium's over on the left side of the periodic table, bromine's over on the right side of the periodic table. Ionic. How about CO2? That's kind of on the upper right-hand side of the periodic table. For carbon, not too far, about 2 spaces away from it is oxygen. This is right side and right side. This is a covalent covalently held molecule. So that means it's a molecular compound. Magnesium fluoride, that's left side, right side, meaning ionic. CH4. Now this gets a little dicey. If the hydrogen is listed second in the molecule, usually that means it's going to be covalent. Okay, hydrogen can actually share electrons and make a covalent bond, which would be a molecular substance. Hydrogen can also form an ionic bond by giving up its electron or taking in something else's electron. So if hydrogen is first, then it's typically, but not always, usually ionic. So in this case, it's second. So that means we have two right side elements. So covalent. Alright? When we're naming compounds, the easiest way to do this is just look at the ions involved. What we're going to do is we're going to look at the first thing in the formula. That will be the cation. We always list the positive ion first in the formula. Okay? What we do is we name that exactly the same as the element. Okay? So if we have NaCl, we start to name this just by naming the cation. Sodium. If it was by itself as a positive charge, we'd want to make sure we said that this is sodium ion. It's by itself and it has a positive charge, as opposed to sodium not connected to anything with no positive charge. That's just sodium, the element. Right, but it's got the charge, it's an ion. This one has a charge, that's why it's attracted to the chlorine, which also has a charge. So we just name the element for the first one. Now, for the anion, the nonmetal, we take the base of the element's name. So for chlorine, it's chlor. And we change the ending to IDE. Okay? So sodium chloride. Voila. So that's how we name ionic substances. So NaBr is sodium. First one doesn't change. Brom is the second one. It's the anion. Ending from bromine changes to bromide. Magnesium bromide, we actually have a +2 magnesium due to how many valence electrons it has. And the bromines are -1 each. There's 2 of them. That gives us a total of +2 and -2 for the 2 halves, the positive and the negative half of the compound. That's why they form this particular ratio of 1 to 2. We'll get more into that later. Don't panic. But in any case, we don't name it any differently just because it has 2 bromines. We say magnesium bromide. That's it. So ionic compounds, we don't have any kind of prefixes or way that's indicating the number of each type of atom. We don't care. We just name it and we go on. Okay, so here's some ions, some common symbols for them. Here are the names. If you want to read through these, just pause it, look through, voila. So let's name these. We have first element. You want to memorize these atomic symbols and names. So you can name each of these just by looking at it. I am going to let you use a periodic table with the names of the elements written on it for all tests. And you can certainly use it for quizzes and homework. But if you don't have them memorized, it's going to take you a lot longer and you're going to run short on time on the exams, which you don't want to do. So lithium is the first element. It doesn't matter that there's 2, we just still call it lithium. Ox is the root of oxygen. Ide says that it's part of an ionic compound, and this is the anion, or negative part. So lithium oxide is the name of the first one. Same idea for the second. Calcium bromide. Calcium bromide. Ki. Potassium for K. That's the cation because it's listed first. Iode. It's the start of iodine. Ide says it's an ionic substance, and it's the anion portion that we're describing. So potassium iodide. You can also have something called polyatomic ions. That means that we have a couple of atoms covalently bonded together, but when they're covalently bonded together, that covalent compound then stole or gave up some electrons to become charged itself. We give those special names. Here's one, carbonate, for instance. Bicarbonate, it's just HCO3. Sodium bicarbonate and sodium carbonate, these are baking soda and baking powder. Nitrates and phosphates and sulfates, those are very common in everything from fertilizer to preservatives in food. And hydroxide is what makes things alkaline, like drain cleaners and that sort of thing, caustic ingredients. But you have to memorize these, so put them on note cards, that sort of thing. You want to be able to know what these different formulas refer to so that you can name them when you see them in a formula. Let's give that a try. Okay. Same rules, it's an ionic compound. Name the cation. Magnesium, the first one. This combined molecule is the hydroxide anion. We know that from the previous table, and we're going to memorize it. So we just say hydroxide. That's the name of the anion. It already has the ending changed when we learned the names of the ions, so you don't have to get any more complicated than that. Second one, sodium. SO4 is sulfate. So this compound is sodium sulfate. So how do we decide what the charge of these different ions will be? The charge is what determined that magnesium chloride actually had 2 chloride atoms for every 1 magnesium. It's what determines the ratios that exist between atoms in ionic substances. So in order to figure that out, though, we have to be able to know what the charges are that are setting up those ratios. And there's an easy way to do it with the periodic table. Let's look at the first column in the periodic table. Lithium, for instance, has a valence electron, 1 valence electron, that is in its outermost shell. If it could lose that valence electron, then it would have the same electron configuration as helium, a noble gas. There'd be 2 electrons in the n equal to 1 orbit, and that would be stable. So if it does that, it's going to be a +1 ion, because it just lost 1 electron compared to the number of protons it had. Sodium also has 1 valence electron. It's the n equals to 3 valence electron, but if it loses an electron, it becomes just like a noble gas neon, which has n equals to 8 electrons as its valence electron orbit, which is stable. So it wants to lose 1 electron then, and again, become a +1 cation. In fact, because all of these elements in the first column share the fact that they have 1 valence electron, they're all going to be +1 ions when they form ionic substances. From very similar logic, everything in the second column, columns are up and down, beryllium, magnesium, calcium, strontium, barium, radium, will all form +2 ions because they want to lose 2 valence electrons in order to be like the nearest noble gas. It's easier to do that than it is to charge across the periodic table and pick up 6 more electrons to have 8 the other way. Okay? So boron is going to be +3 because of the number of electrons it has. It's going to want to jump back, lose 3 electrons, and have the exact same configuration as helium now. And if it loses 3 electrons to have a noble gas type configuration which is stable, it'll be +3 ion. Now, carbon, if it forms an ionic substance, which it can form +4 ions because it wants to lose 1, 2, 3, 4 electrons to be like a noble gas, helium. But it could also gain 1, 2, 3, 4 electrons and have the same configuration as neon does, also a noble gas. So because it could gain 4 electrons, it could also be -4. Right, now it has 4 electrons more than it started with. So nitrogen is closer to gaining 3 electrons and being like neon than it is to losing 5 electrons and being like helium. So everything in this row can only be -3. Only the carbon, silicon, germanium, tin, lead, only those are really the +4, -4 ions. Oxygen and everything under it forms -2 ions. Everything in the halogen column, fluorine, chlorine, bromine, iodine, astatine, forms -1 ions. Right? It has 7 valence electrons in each of these elements. All it has to do is gain 1 electron to be like the nearest noble gas, and that's it. You might be asking, all right, that's great. What about all the transition metals? It actually varies. A lot of them can have more than one possible charge. They can be +2, +3, some of them are +6, +4, all sorts of different possibilities. Predicting that is beyond the scope of this class. And we won't be asking you to predict what causes the different charges or memorizing anything about the different possible charges for these transition metals when they become ions. Alright, so let's put some together. Sodium chloride. To make the chemical formula, we look up the periodic table, ion, or the atomic symbol for sodium and for chlorine. Right? Remember, chloride is just the ion substance for chlorine. We give a little bit of space so we can put subscripts if we need to. And then from the periodic table, we look at whether these ions will be +1, -1, +3, whatever they're going to be. So in the periodic table we just wrote, we saw that sodium is going to be +1, because it's in that first column. Chlorine will be -1, because it's in that almost last 17th column of the periodic table. So because +1 and -1 exactly equal each other and cancel out already to give me a neutral ionic compound, which is what we want to do when we combine ions together. We want to get to neutral because then they won't attract any more ions. They'll stay at whatever ratio they're at. So 1 to 1 is the proper ratio. And remember, we assume there's a 1 there if we've written the symbol. We don't have to draw a 1 subscript next to either of these things. So NaCl is the proper formula for the thing that has the name of sodium chloride. Magnesium, chlorine, a little bit of space. Magnesium is +2 according to where it is on the periodic table. We already said chlorine is -1. So in order for this to work out, we're going to need 2 chlorines. So that way we'll have a total of -1 times 2. Of 2 -1 ions, or a -2 charge for the 2 anions that we have. We have 1 magnesium at +2, so +2 and -2. Again, we have a 0 net charge, but only if we put a subscript here to make this balanced in terms of the overall positive and negative charges present in that particular unit. So that tells us then that the proper formula for magnesium chloride would have to be MgCl2. Okay, so just simplest whole number ratios here. Calcium oxide, CaO, a little bit of space so we can draw some stuff in. Periodic table says we have +2 and -2 respectively. These are balanced already. Boom, done. That's it. Calcium oxide is just CaO. That's its chemical formula. So we can translate the names into the ratio of atoms just from the names. And our overall goal in this semester is that I'll be able to give you a name, then you'll be able to come up with a formula. From the formula, you'll be able to predict how it's attached to each other, the different atoms are how they're attached. From how they're attached, you'll be able to tell me what shape the molecule exists in. From the shape, you'll be able to tell me how the forces are that interact between one molecule and the next. And from how those forces are, you'll be able to tell me all about the chemical properties of that molecule. So ultimately, what I want you to be able to get to for this chemistry class is to go directly from the name through a few steps to understanding and knowing the chemical, or at least relative chemical properties of that substance, just from knowing the name. That's what we do in chemistry. Let's look at some more examples. Lithium oxide, lithium, oxygen, +1, -2. So I'm going to need 2 lithiums. So 2 times +1 gives me a +2 total. -2 times 1 gives me a -2 total for the oxygen. I combine these things, I get 0. That must be it. Li2O is the formula for lithium oxide. We can do this just as well with polyatomic ions. Magnesium hydroxide is OH. Magnesium is +2. Hydroxide is -1. We know that because we have to memorize that from our list of polyatomic ions. Now when we have -1 and we need 2 of them, we need 2 of the whole unit, the whole hydroxide. So we literally put parentheses around the whole hydroxide, and then we put the 2 that we want to say there's 2 hydroxides, so we put a 2 on the outside subscript of the parentheses. That's saying 2 of this whole unit. So now 2 oxygens and 2 hydrogens, and each of the oxygens and hydrogens are bonded together as a unit. So that gives me a total of -1 times 2, or -2. Magnesium is +2, 0 net charge again. So the chemical formula is Mg parentheses OH close parentheses 2. That's magnesium hydroxide. Okay, calcium phosphate. Calcium, Ca, phosphate, PO4, another polyatomic anion. Calcium is +2, phosphate is -3. So to get this to work out, we kind of go back and forth a little bit. Find out we need 3 calciums and 2 phosphates. Why? That's my parrot again, sorry. 3 times 2 gives me a total of +6. -3 times 2 gives me a total of -6 for the phosphates. So +6, -6, 0 total charge. So this ratio of Ca3 parentheses PO4 close parentheses taken twice is the chemical formula for calcium phosphate. Alright, we're all over this now. So naming molecular compounds, that's going to be a little different. They share electrons, so they don't really go together based on any kind of charges. In fact, they don't have charges. They're not giving up electrons, they're not taking in electrons, they're sharing them. So they're not positively charged, they're not negatively charged, meaning that they won't form those kind of ratios. I can have, for instance, a compound CO, carbon monoxide. I can have another compound with just carbon and oxygen in a different ratio, CO2, and that's called carbon dioxide. So you can kind of hear it, but what we do is name the more metallic all that means is the one that's on the left side in the periodic table, the one that's more left-hand side. And we say that one's first, and then when we name it, all we do is just say that's the name of the element. Okay? What we do for the second element in the compound is we list it second. That's the one that's farther on the right relatively. And again, we're going to treat it just like it's an ion, even though it's not. And we're going to change the ending to IDE. Now, because we can have different numbers of each of these elements, and they form totally different compounds with different properties, carbon dioxide isn't good, but it's not too highly toxic, especially in small amounts. But carbon monoxide binds to your hemoglobin very effectively and doesn't really let go and prevents oxygen from circulating through your system. So carbon monoxide is highly toxic in relatively small doses. So just a slight difference in chemical formula gives you vastly different chemical properties. So we need to be able to differentiate between these two just by what they're called. So to do that, we tell how many atoms there are by just basically saying the number of atoms, but we do it in Greek because making it confusing ensures job security for chemists. You laugh, but that's pretty much the only good reason for this. So we have some prefixes. We have mono, which means there's one of them. Di, two, tri, three, tetra, four, penta, five, hexa, six, hepta is 7, octa is 8, nona is 9, and deca is 10. There's names, of course, for things beyond 10, but we're not going to get into that. This will cover us. One rule that we have to keep track of is to kind of make this a little bit less awkward to say if the first atom is only has one of them, like in this case where we have one carbon. We wouldn't call this monocarbon monoxide. We just leave out the mono for the first element. We'd still use di and tri and tetra if there were 2, 3, or 4 of the first element. We just don't use mono for the first element. That just makes things less awkward. So CO is carbon, O for oxygen. Oxygen becomes oxide. There's only one of them, so we call it monoxide. Notice how we dropped the second O, because we had MNONO-OXIDE. It would have been a double O. That would be awkward, so we just dropped that. You'll get kind of a feel for which times we drop the vowel and which times we don't as you kind of go through this and get more used to it. But for now, just kind of give it your best shot, and I'll grade you accordingly. So carbon monoxide is this first compound, saying there's a carbon and there's one oxygen attached to it. The second compound, CO2, first element, carbon, written as is, 2 oxygen, second half, so oxides, 2 di, oxygen, ide. That's the second one. Carbon, di, oxygen, ide. Second element. Okay, so that's how we puzzle through this sort of greatness. Let's try a whole bunch of these, make sure we got a good handle on it. We just did this one, right? Pause, try it. Carbon monoxide. Right? Second one. 2 nitrogens, so we have to say di-nitrogen. Okay, because there's 2 of them. We have to say di. The only time we don't put a prefix on the first one is if it's mono, and it's not in this case. And then we have 5 oxygens, so penta is 5. It would be AO, a double vowel, so we drop the A and say pent. Ox, that's the second element, so we say ide. So 5 oxygen second element, pentoxide. So this compound is dinitrogen pentoxide. SO3, sulfur. We don't put mono. Tri for 3 oxygens, ox and ide. Sulfur trioxide. Excellent. Now formula mass. Just like we can calculate the atomic mass of an element, what that element's atoms weigh, either in AMUs per individual atom or grams for every mole of those sorts of atoms, we can also just add up the weight of each of the atoms in a compound, and for ionic compounds we refer to that as the formula mass, or the mass of the simplest unit of that crystalline lattice of repeating sodiums and chlorides. And we do that just by looking at the periodic table again and finding the atomic mass, and then we take the atomic mass and multiply it by the number of that particular element appearing. Right, so sodium provides us with 22.99 AMUs of mass. The chloride ion provides us with 35.45 AMUs for each, and there's only one, so 35.45 AMUs. We add this together, we get 58.44 AMUs, and that's per sodium chloride. We could also say that there's 58.44 grams, which is much easier to measure than an AMU, right, for every 1 mole of sodium chloride units. And so this is called the formula mass, which is a ratio of mass to number for ionic substances. The molar mass is the exact same thing, but for other compounds. So molar mass, we can just say mass in grams per mole. The book kind of talks about this a little bit oddly. It refers to molar mass in terms of any compound but in grams per mole. More typical usage is that molar mass and molecular mass is how we refer to the mass of grams per mole, or AMUs per unit, for covalent compounds, molecular compounds. And formula mass is what you use to represent ionic compounds. In a practical sense, they're both used in exactly the same way. They're just slightly defined differently, but they're calculated identically, they're used identically. So let's look at this particular compound, which actually has covalent and ionic bonds. It's covalently attached CO3 carbonate, and then the carbonate is an ion attached to a calcium, so that's an ionic bond between the two chunks here. In any case, the periodic table says 40.08 grams for every mole of calcium underneath the symbol for calcium, and there's one of them. So we have 40 grams towards the total weight for that. 12.01 grams for the carbon. 16 grams for each oxygen, and there's 3 of them, so 48 grams total there. And we get a total of 100.09 grams of calcium carbonate for every 1 mole of calcium carbonate units. We can use this as a conversion factor to convert between grams of a substance and the amount of that substance, the number of moles of it, or vice versa. So let's look at H2S. So pull out your periodic tables. We'll take a look at the mass of these two substances. Hydrogen, for instance, is about 1 gram per mole. You can use more digits, but there we go, about 1 gram per mole in the periodic table. It's actually like 1.079, but whatever, 1. Sulfur is about 32 grams per mole on the periodic table. So we add this up, we have 2 hydrogens, and that 2 subscript. We have 1 sulfur. So hydrogen sulfide gas, it would be 34 grams of hydrogen sulfide for every 1 mole of hydrogen sulfide. Pretty straightforward, right? All right, well, what if we want to look at amounts of substance? All right, well, we just calculated 34 grams of H2S, hydrogen sulfide, for every 1 mole of hydrogen sulfide. So if we are going to consider this mass and try and calculate the amount of molecules in that mass, first thing we need is this conversion factor so we can use it. And then we use that the same way we would feet to inches, inches to miles, whatever. We say we have 10.0 grams of hydrogen sulfide, and then we're going to multiply that to get to the number of molecules in that. Well, we know the ratio between moles of molecules and grams, and we know the ratio from before between individual molecules and 1 mole of molecules. So let's just work this out. The grams of hydrogen sulfide gas need to cancel, while moles of hydrogen sulfide gas need to be on top. This conversion factor says 34 grams for every 1 mole. We can multiply this out and get an answer, but we'll just keep going. Grams of hydrogen sulfide gas have canceled, and we're left with moles, which I've written twice cleverly, moles of hydrogen sulfide gas. So if we wanted to go from moles to molecules, that's this ratio here, Avogadro's number, 6.022 times 10 to the 23rd power of molecules for every 1 mole. So moles cancel, and we're left with molecules of H2S. And so we can plug this through on our calculators and get a number for this. Let's see if I can pull up a calculator real quick. There we go. Unhappy bird. Oh, we already have a scientific calculator. Alright, so 10 grams times 1 divided by 34. Okay, that's how many moles of hydrogen sulfide we have. That's stopping right at this portion, right? There it is. Now we take this and we multiply it by, oh, there's multiplying. Multiply it by 6.022 times 10 to the power of, here's the EXP key, that takes the place of times 10 to the power of 23. And we get, wow, a really big number. Really? It couldn't display that in scientific notation for us? That was rude. Alright. This is why you get a real calculator instead of using these. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23. So 1.77 times 10 to the 23rd power. 7 times 10 to the 23rd power. Excellent. Okay, so that's as hard as that is. So we've used chemical formulas as conversion factors. We can use that also within the same molecule. We can say there's a certain number of atoms in one water molecule, for instance. All the time we've done this sort of thing. You know that there's 4 tires on a car, for instance. So if you want to find out how many tires there are on 5 cars, you're actually just using this conversion factor. 4 tires for 1 car. Cars cancel, and we're left with the units of tires. 20 tires. Same idea. If we want to know how many hydrogen atoms there are in some number of water molecules, let's say 10 waters, how many hydrogens are there? We say there are 2 hydrogen atoms for every 1 water molecule. It's going to give us 20 hydrogen atoms. And so these formulas, the chemical formulas, gives us the ratio between the different types of atoms in that particular compound. And we can use that like we use any other conversion factor if we need to. So let's see. Let's do the same kind of thing. 5.25 grams of hydrogen sulfide. To answer this first question, how many molecules of hydrogen sulfide are contained in the sample? We know how to do that. We just did it. 5.25 grams of H2S times 1 mole of H2S for every 34 grams of H2S. All right, now we're in moles. These grams canceled, and moles are what's left. To individual molecules, we can just put molecules on the top. Over 1 mole on the bottom. Moles cancel. We're left with molecules of H2S, which is what we want. How many molecules of H2S are contained in that sample? Molecules H2S. We pull out our calculator. Start typing in numbers, huh? Alright, 5.25 divided by 34. That's the number of moles of H2S we have. Each mole having 6.022 times 10 to the 23rd power. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Alright, so we have 9.2, oh shoot, what was that? 9.29 or 9.30. 9.30 times 10 to the 22nd power molecules of H2S. Alright, well that's good. But how many moles of hydrogen atoms are present in that 5.25 grams of H2S? Same idea here. I get one step at a time closer to my answer. If I know the count number of hydrogen atoms, or of H2S molecules, I can use the 2 hydrogen atoms for every 1 hydrogen sulfide molecule ratio, and I can calculate this answer out. So 1 mole H2S every 34 grams of H2S. This is going to give us 5.25 divided by 34.154 molecules of hydrogen sulfide. Okay, so we're almost to the answer. 0.154 molecules times of H2S times 2 hydrogens every 1 H2S. Yes. These two things cancel out. Right, that should be on the top, not on the bottom. I just ran out of room. Hydrogen molecules, or atoms, are what we have left. So we get 0.308 molecules, or actually just moles. Hydrogen isn't a molecule. 0.308 moles of hydrogen. And that's our answer. So now we can answer other questions like how many grams of sulfur are in the sample. Alright, well, our first step again is to get to moles. Because we can't change from one substance or one part of a substance to another in weight, because the different atoms weigh different amounts. We can't directly compare that way. But once we turn it into a count, an actual raw number of these particular compounds, molecules, then we can switch back and forth of the number of the different types of things present. So 5.25 grams, 1 mole of hydrogen sulfide for every 34 grams of hydrogen sulfide. Lo and behold, it's still 0.154 moles of hydrogen sulfide. Now we're going to take that 0.154 moles of hydrogen sulfide, and we know we can find out how many sulfur moles there are by saying that there's 1 sulfur for every 1 hydrogen sulfide. So that means 0.154 moles of sulfur are present in that 0.154 moles of H2S, which is 5.25 grams of H2S. And now we can just turn that into grams. By multiplying, and we want grams to appear, so we say 32 grams of sulfur for every 1 mole of sulfur atoms. So moles of sulfur cancel, we're left with grams, and we pull out a calculator, multiply by 32, you should get something like 4.94. 4.54 grams, 94, sorry. 4.94 grams of sulfur. And so most of that sample is sulfur. There's a little bit of hydrogen in that 5.25 grams, but most of it looks like it's sulfur. Now, chemical reactions are the last thing we're going to talk about here in this chapter. This is how we talk about chemical changes occurring. One substance or multiple substances turning into a new substances or new multiple substances. Now we do that by showing the chemical formulas of the reactants. That's the stuff we start with. Call it reactants. We put that on the left-hand side. Plus means we also have this particular species, oxygen, diatomic molecule, methane, which is CH4. We'll talk about how to name those another time. And these reactants then, arrow, meaning turn into the products, which are everything on the right side of the reaction, which in this case are carbon dioxide and water. These coefficients means I have 2 waters, 2 molecules worth of water every time I get, ratio-wise, 1 carbon dioxide made. And again, this 2 over here means I need 2 oxygens to react with 1 CH4, turn into carbon dioxide and water. And the reason we have to have these 2's here is otherwise it doesn't add up. We don't have the same number of each type of atom on both sides of the equation. And the law of conservation of mass says that we can't get rid of atoms and we can't create atoms. So we have to figure out the ratios involved so that we're not saying that that is occurring. Once we have those ratios, we can use those ratios for another set of calculations. Okay, but let's look at that. If we have the unbalanced equation and we're not given the actual balanced equation, I look at this and say, all right, I have 1 carbon and 1 carbon. Carbon's balanced. I look and say I have 4 hydrogens and 2 hydrogens. That's not balanced. So I'm going to need 2 units of whatever molecule is providing the hydrogen, which in this case is water. So I'll put a 2 coefficients in front there and say I have 2 of those. Now water is the compound made. It has the physical and chemical properties of water. That's what it is. We can't change or play around with the subscripts because that would change the chemical identity of that species. The coefficient number in front only says that we have 2 of those waters. Okay? So once we put those extra 2 on that side, now hydrogen is balanced. When we've done that though, or at least actually before we did that, when we only had 1 oxygen, we had 1, 2, 3 oxygens originally before we added the 2 coefficient. And that wasn't balanced with the 2 oxygens on the left. But now that we have this 2 here, what we actually have is 4 individual oxygens on the right-hand side, right? 2 times the 1 oxygen in each water. 2 more oxygens because of the O2 in carbon dioxide. But on the left side, all I have is 2 oxygens. So I have to add a second unit of O2. Now we're balanced, and now this looks like this. This is what we refer to as the balanced chemical equation. We change the number of them that are reacting. And this says that there's 1 methane molecule needs 2 oxygen molecules to react. When they do, they're going to form 1 molecule of carbon dioxide and 2 molecules of water vapor. So here are some tips on how to balance. Don't use fractions. If you find that you've used fractions, get rid of them by multiplying everything by some common number. But overall, these are the steps. This is the most important one, is use coefficients, but never use subscripts. Alright, so C3H8, often used in the place of methane for heating. It burns with the oxygen, so we're saying C3H8 burns, chemically combines with oxygen. It's one of the diatomic molecules, so we know it exists as O2 in the natural state. It says it then makes carbon dioxide and water. Excellent. Now we have to balance it. Right, 3 carbons, 1 carbon, and I have to write 3 in front of this carbon. 8 hydrogens and 2 hydrogens means I need 4 water molecules. So I have 4 times 2 is 8 hydrogens, and 1 times 8 is 8 hydrogens on the left. So now hydrogens are balanced. Well, pardon me, late night. Now the only thing we have left is that we have 2 oxygens, and here we have 3 times 2 or 6 oxygens plus another 4. So 4 oxygens. So 10 oxygens altogether. So that must mean we need a 5 in front of this O2 so that we'll have 10 oxygens on this side as well. Okay, so that's how we figure out the balanced chemical equation says that for every propane we need 5 oxygen molecules and we get 3 carbon dioxides and 4 water molecules. Yep, that's what we just did. So we can answer how much questions exactly the same way as we did with the previous problems where we worked out how many atoms or how many grams of a certain type of atom are present in a compound. So let's look at this. I have this Haber process, which is nitrogen and hydrogen making ammonia, NH3. It has a common name of ammonia. We've balanced it for you already. We have 11.5 moles of hydrogen gas. Then we're going to have as much nitrogen as we need, but we want to figure out how much nitrogen we need to have the proportional amount of hydrogen and exactly use up all the hydrogen making ammonia and not wasting any. Okay? So that means these have to be equivalent. We can do that with the balanced chemical reaction if we can say that there are 11.5 moles of H2, that's what we were told, 11.5 moles of hydrogen gas, and now we can multiply just by the how much nitrogen is made. 1 nitrogen for every 3 hydrogen gases. So this will cross off the hydrogen, we're left with moles, nitrogen, we got the 1 and the 3, and the 1 here, and the 3 here. When we multiply this out, all we have is 11.5 moles times 1 nitrogen over 3 hydrogens. All we have is a third of this, which I'm not going to try and calculate by hand. Right, so 11.5 times 1 divided by 3 is something I should have calculated when I had the calculator up. 11.5 divided by 3, 3.83, etc. Units are moles. Gotten rid of hydrogen. We're left with nitrogen. So my 11.5 moles of hydrogen will use up and need exactly 3.83 moles of nitrogen in this reaction as ammonia is being made. And so basically, the summary is this balanced chemical equation is just our recipe card here. The conversion factors that we can get from it with the balanced coefficients just give us more equivalencies, more conversion factors to use to calculate things. Just remember, if we're in grams, the chemical equation doesn't give us any ratio in grams, it gives us ratio in counting numbers. So moles would work, grams will not. Okay, so if we want to go from grams to something else, that means first we have to turn into moles. Okay, so our strategy is, for this problem, and you can pause it and read it, but our strategy is that we're going to say we have this certain amount of methane, 2.13 times 10 to the 8th grams of methane. We want to convert it to water vapor. So somewhere over here, we're going to have grams of water vapor. And we have all sorts of ratios here. We know there is a 1 to 2 ratio between methane and water, and vice versa. It's a 2 waters to 1 methane as well, but that's fine. We know that we have 12 grams per mole for carbon and 1 gram per mole for hydrogen. So that's 12 plus 4, 16 grams per mole for methane. That's the molecular weight of methane. So that means we can convert from grams of methane to moles of methane just by putting the grams on the bottom and the moles on top. Right, so 2.13 times 10 to the 8th divided by 16 grams of methane cancel, and we're left with moles of methane. Well, we want grams of water, so we can again get one step closer and say that there are 1 assumed mole of methane for every 2 moles of water. Now here we want to end up with water, so we put water on the top and say that there's 2 of them for every 1 methane. And we get whatever this first number is times 2, or twice as big. That's converting from moles of CH4 to moles of water. We have to be in moles to use the coefficients in the periodic table. And now our units, CH4 cancels, and our units are now moles of water. We own the house, but we can't own the house. All right, I don't know where that came from. Oh, yeah, sorry, I have absolutely no idea where own the house came from on that comment. I totally misspoke. We have calculated out our current answer in terms of moles of hydrogen, and we can pull the calculator up and look at that. Say 2.13 times 10 to the 8th, divide by 16. This is the value in terms of the number of moles of methane that we currently have in our calculation. So that's right here. Now we multiply that by 2 because there's twice as much water as methane. According to what? According to our balanced chemical equation. Yes, we have about 26 million or so moles of water. And now we want to go back to grams. So we say 2 hydrogens at 1 apiece is 2 grams. 1 oxygen at 16 grams. So that's 18 grams of water for every 1 mole of water. It's molecular weight of water. Moles are what we have currently, so that has to go on the bottom. 1 mole of water. Grams are what we want, so grams of water goes on the top. So that means we just multiply that number we had before times the 18 grams for every 1 mole, and we get this bigger number. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 4.79 times 10 to the 8th power. So many grams of water are produced by that town burning methane. Alright, so go ahead and do lots of practice. You can look up what's called stoichiometry. That's what we just did in that last example. Stoichiometry. And find worksheets on those sort of problems online. There's hundreds and hundreds and hundreds of them. There's tons in your book. There's some in the homework. Won't be a difficult time finding them. But we talked about the difference between chemical and ionic compounds, formula and molar mass. We looked at chemical reactions and chemical equations and how to balance them. And we talked about the different parts of those chemical equations and reactions, including reactants and what they turn into, which is products. The chapter also talks about different compounds, gives you a little bit of a background on some of the compounds that we have and how some of them are important or detrimental to the environment. The book also talked about how we have all of these chemical reactions going on in our society in terms of making things like fertilizers or plastics or other different compounds. Those all come into different reactions that turn basic reactant substances or raw materials into finished products. And our bodies basically do the exact same thing on kind of a more biological basis, but it's still chemistry. And that's it for Chapter 4.